So what can you guys tell me, or what do you think are two factors that will dictate how things actually come together to form bonds or break bonds? All right, temperature can have it, so that's kind of, what does temperature measure, guys? It's a review question. Energy, right? What type of energy? Kinetic energy, guys. So with collision theory, all right, just kind of add it there at the bottom with that fill in the blank, all right? Particles must collide. This is, again, for a reaction to actually occur, and they have to have the following when they do so. Okay? And the first one, like we said, is the proper amount of energy. Okay? So they have to have enough energy. If they don't, they're not going to break the bonds, because what's in bonds? Like, what's in a bond, guys? What holds a bond together?
Electrons.
Electrons are in there, which, do electrons want to stay close together? No, because they're what? Same charge, they're negative, they want to repel each other, so what has to hold them together? It's what we just wrote down. Energy, right? It's all about those energies. So they have a lot of energy holding them together. If they don't have, the particles, guys, when they're reacting, they're colliding with each other, if they don't have enough energy to overcome the energy that's in the bonds to break them, nothing's going to happen. They're going to stay where they are. Okay? What's the other piece do you think they have to have? This is one that maybe we kind of briefly mentioned, which is why we're coming back to reiterate that, guys, and that is proper alignment / orientation / direction. Okay, kind of all mean the same thing. Right? Meaning they have to be aligned just right in order for them to come together. So when we talk about organic a little bit later on, toward the end of the year, guys, we'll talk about these things called isomers, where they are just basically same structures or same formulas, but they have different orientation, different arrangements of the atoms, okay? And based on how different particles and different molecules and compounds are arranged, they may or may not want to react together. Or they have to move and shift, and that can make a longer step to make the reaction take a little bit longer. So just remember those two things, guys. Collision theory is kind of summarized in those two things. You've got to have proper energy and proper alignment for reactions to really take place, okay? So let's talk about these 6 factors. Why don't we go through and have you guys kind of tell me what you found. What are the 6 factors? You didn't get to that. Surface area is 1. Concentration. Somebody else besides Garrett. Temperature. What else? The nature of the reactants, which is kind of like the state of matter. There's pressure, which only affects what? No, not. I mean, they might go hand in hand, but what's the only state of matter, guys, that pressure is really going to affect? Gas, right? Because it's something that measures in pressure. And then what's the last one? Catalyst, okay? I don't care, guys, what order you have them in. Okay? It doesn't matter which order, just as long as you have the information. We're going to take them one by one, so if they're not in the same order that I have, that's okay. All right? So, we want to be thinking about how the rate is affected with each piece, and then why does it increase or decrease the rate, okay? So the first one, guys, that I have is the nature of the reactants. All right? And by nature, we're talking about what type of bond. Okay? What type of bond? You can also think about state of matter in there. I'm trying to think. Let me check my notes really quick. A lot of times I also, guys, when I think about the nature of it, it's not just the bond type, but it's also what state of matter. Okay? Which state of matter do you think is going to react the easiest or the fastest? Why gases, Alex? Yeah, they're spread out and they're moving faster, so they will typically react faster. Whereas solids, guys, the particles are very close together, and they are connected and they're stronger. They're held together a lot stronger, and that kind of goes right along with ionic and covalent, guys. Now, this we're talking about. Ionic substances will react faster. Covalent ones will react slower, because if you think about it, guys, what do ionic compounds form? Salts. All right. What else? Do they stay together in solution? No, what do? They form says it right up there. We've done it all year, guys. What do ionic compounds form? Ions, right? Ions. So they break apart. All right, that's the big idea, guys. Ionic, they're smaller, less bonds to break, less steps. So we can see something like that reaction there is just as an example. You don't have to write all of that in there, guys. For the why does it increase the rate? All right. Well, you need to make sure, guys, ionic are smaller, so they have less bonds to break and they have less steps. Covalent are larger. They have more bonds to break, which means more steps. All right. Covalent, if you think about it with covalent, guys, a lot of organic compounds that we're going to talk about, you'll see just how large they are. They take a while to break those bonds. So they can take, I know when I was in grad school, even when I was an undergrad, and I took organic chemistry and I had organic lab, some labs would take 4 hours or more because the reactions take that long. I know in grad school, people who worked in the lab down the hall from me who were in organic synthesis labs, they might have taken 12 to 24 hours where they were just in reflux, where they were just letting it mix and letting it react all on its own. Okay? So they would just have to set it up in the lab, leave it overnight, and come back, and it would still be going, waiting for those reactions to occur. They have a lot more complex structures, so it takes a lot more energy, and that orientation piece comes in there when you have a more complex structure. Okay? So the big thing, ionic are smaller. Like you guys said, salts. We have that ionic crystal, right? That crystalline shape where you alternating positive and negative charges. It makes it a little easier to break those apart. And when you get them into solution, then you have the ions there. Where covalent compounds, guys, like glucose, does that break apart in solution? No, it dissolves. So you don't have as big of crystals, but it still stays together as C6H12O6 molecule. It doesn't break apart into, like sodium chloride would, into sodium ions and chloride ions. All right? Good here? Questions? Number 2, concentration. Now, guys, this should hopefully be obvious to us because what does concentration measure? No, it doesn't measure viscosity. Oh, my goodness. Moles per liter, right? That's molarity. But guys, the more of something you have present, the faster the rate is going to go because you have more things interacting. So if you increase the concentration, you're going to increase the reaction rate. So the more particles in a given space, the less space between them, the more collisions. It should be kind of common sense there. All right, number 3 is pressure, like we talked about. Now remember, make yourself a note, guys. Pressure only affects gases. So side note, this one is only specifically for gases. If we increase the pressure, what's that going to do to us? What does that do to the size of our container? Right, so you go from something like this, or if you had like a piston on this, you have all these gas particles rearranged and kind of spread out. If we increase the pressure, we make the volume smaller, so they start to interact and they get much closer together, more collisions. All right? Increase that pressure, decreases the volume, which decreases the space, more collisions. If you want to draw a picture there to help you get it, whatever it takes, whatever you guys need to help remember. Temperature. Again, guys, if we increase the temperature, what's that going to do? It's going to increase the rate. Why? If we increase temperature, guys, what do we increase? The amount of energy, which increases the speed, more collisions, and you have more energy within those collisions. Particles are moving faster with more energy. It's a double boost. Area. We actually already looked at this. Remember when I broke up the Alka-Seltzer tablets? Right, we threw a whole tablet in there versus the powdered one. Okay, which one reacted faster? The powder. Why? Increased surface area, guys. Again, you increase it by spreading it out more. You have more chances for those particles to interact. All right, whereas if you hold a sugar cube together, only the outside of that cube is going to dissolve first. It's kind of go from the outside all the way in. It's much slower. Where if you break it up or have something like granulated sugar, it's going to be a lot faster. So the increasing it, the more reactant particles you have, you're exposing it more so that they can react faster. Okay, and that's just kind of a little graph there. Don't bother putting that in your notes. Just showing you how you're increasing it. You have more surfaces. Good. And the last one, like we said, it was a catalyst. Now, when we start talking about potential energy diagrams here in a second, guys, we will talk specifically. You know from past science classes that, hey, a catalyst, yeah, what does it do? It speeds up a reaction. But the why behind it is very important, and that's what we will talk about and look at. What it does is it provides a shortcut, guys, or an alternative pathway for the mechanism, which in turn lowers the activation energy for the reaction. You probably are like, what in the world does that all mean? It'll make more sense in a few minutes once we start going through potential energy diagrams, okay? Remember, catalyst, guys, it's there, but it's not changing or taking part in the reaction. It's just to help lower that energy. All right. Potential energy diagrams, guys, all of those 6 factors are different pieces that kind of go along with the reaction pathway to kind of speed it up and try to help that get going. So we're going to talk about now these diagrams. So the recall part, guys, the paragraph, you don't have that in your notes. You don't need to write it down. Okay. We've talked about chemical bonds, guys, throughout the year. They have stored energy. What is stored energy called? Potential. For that reason, guys, chemists will use potential energy diagrams to illustrate it. Now, it's just showing what's happening with the energy. Okay? So it's not necessarily specific. It's more in general. So keep that in mind as we go through that. So a reaction, guys, again, we should know it's you're breaking and reforming different bonds. We talked about heat of reaction, or delta H. What's another term for delta H? Starts with an E. Enthalpy, right? Enthalpy is the same thing. All right? It's the amount of heat energy that's lost or gained throughout a reaction. Remember, delta H. This, I don't think I wrote this down in your notes yesterday, guys. Okay, circle it or something like that. This is how delta H is calculated. It's the heat of the products minus the heat of the reactants. Keep that idea in mind, all right? Products over reactants, or products minus reactants. As we talk about K expressions here the next few days or so and in the next week, that'll be a common theme. Okay? So again, reiterating some different things we've talked about. There's 2 types of reactions, guys. If they release energy, they are what? Exothermic, right? Exothermic. Delta H then is going to be negative. This is what a reaction would look like, guys, if it's exothermic. You have something that indicates energy, and it's going to be on the product side of the reaction. It may just say the words energy. It could also say heat. Or it could be a numerical value. What's our unit that measures energy or heat? Joules. So it could be something, guys, that could say like plus 50 kilojoules. Okay? It could be any one of those 3 things. It could say energy, it could say heat, or it could give you a numerical value in kilojoules, which you've got to know from our past stuff that we've done this year, like Q equals MC delta T, that kilojoules measures energy. So, for example, sodium and water. Maybe when we do review, maybe I'll get some sodium out and we'll do that as a demo in the fume hood. They're in the process of making sure the fume hood's working properly. So after that gets done, then we will maybe test out some sodium and water. We'll throw some in there. Now, reactions, guys, on the flip side that absorb energy are called endothermic. All right, so delta H is going to be positive. This is where, guys, energy is absorbed on the left side, or is as a reactant in your reaction. So again, same thing. You can see it could be plus heat, or plus that 50 kilojoules, or whatever amount of energy as well. So be on the lookout for those, and you'll see what I mean as we get going here today. So an example, guys, baking, oven is supplying energy. If you put all the substances together, are they just going to bake on their own? Maybe on a hot day, you can go out on the street and fry an egg. Anybody ever try that? In Arizona? Yeah. I wouldn't suggest eating the egg, unless you want to eat some like tar. Oh, you put a cookie tray? I didn't even think about something like that. I was just thinking about just literally frying it on. Hey. You try that and get back to me, all right? You try that and get back to me. Now, guys, yesterday we also talked about stability. Okay? Which type of reaction is more stable than the other? What'd you say? Exothermic. Why? Yeah, all the energy, guys, is dissipated. Okay? Exothermic are going to be more stable. All right, endothermic are going to be less stable, because think about it. You're trying to hold in all that energy, all right? It just wants to be released, right? Systems don't want to have a lot of energy. They want to be in the lower energy state. We're lazy. Same with us, right? We don't want to have a lot of energy. We'd rather just be kind of, relaxed and stuff, be a little bit more stable. So think about it. If you have a large delta H, it's more stable. a large negative delta H is more stable. A large positive delta H is less stable. Keep that in mind. All right, whatever you guys do in a chemical equation, you must also do to the delta H. So, for example, if you reverse a reaction, meaning you flip the products and the reactants, then what do we have to do for the sign of the delta H? We have to flip it as well, or make it the opposite. Okay? All right? If you double the equation for the coefficients, what must you do to the delta H? You're going to have to double it as well. Okay? So whatever you do to your reaction, guys, you're going to do that for the delta H as well. Get your reference packets out and flip to table I. Table I, guys, on your reference tables. You've got a list of a bunch of different reactions. And notice what it tells you. It's heated reactions at not STP, but standard pressure, and then at 298 Kelvin, so about room temperature. Okay? So it gives you the reactions, and it only shows the forward reactions, and along with it, you have delta H. So take a look, guys, at the first example that you have there. It's CH4 gas plus 2 moles of oxygen gas yields carbon dioxide gas plus 2 moles of water. Prize question. Who can tell me what type of reaction that is? If you had to identify the type of reaction. This is review from like Unit 7. What type of reaction? You get one yes. Raise your hand for the prize. There's 5 types of reactions we talked about. Grant? No. Not a double replacement. Jill? Nope. Nope. See, that's 3 of them. It's combustion. Oh. It's a combustion reaction. You got carbon dioxide and water. It's not synthesis, right? Why isn't it synthesis?
It's not 2 different.
Oh, what? No, okay, I can see that now. I can see that now. This is dumb.
When did you write that one?
Like 2 minutes ago. Guys, you don't have to write this down. This is the first one that's on table I in your reference packet. Notice they give you the delta H. What type of reaction is this? It says the delta H equals negative 890.4 kilojoules. Okay? What type of reaction would it be? Exo, right? Why? Because delta H is negative. Now, they're giving you the delta H as a separate component. If we were to write it into the reaction, would we write that value as a reactant or a product? Product, okay? So it would be written like something like this. Okay, let me erase that. If we were going to write it all as one reaction, it would be plus 890.4 kilojoules on the right. Now, why is it a plus sign in the reaction? Yeah, it's going to be plus, guys, whether it's a reactant or a product. So even though when it just gave us the value as delta H was a negative 890, okay, this still means the same thing because even though we're saying plus here, it's not saying that, oh, it's absorbing energy. It's releasing it because it's on the product side. Does that make sense, what I'm trying to say there? Okay? So just keep that in mind. If you see it written as a reaction or if they give you a separate delta H, be aware and know what they both are. So here we go. Number 1. These are easy questions. You're going to find the reaction on table I. So number 1, you've got N2 plus 2O2. Now, make sure you're looking at the right reactions. Some are very similar to each other. Okay? So number 1, you're going to look on it. It's about halfway down. Okay, what's our delta H value? Yeah, it's positive 66.4 kilojoules per mole. Is that endo or exo? Endo, right? It's a positive one. I want you guys to go through numbers 2 through 5. When you take a look, guys, 2 and 3 here, they're flipped. Right? So you've got to flip your delta H, which makes this one now a positive 91.8, which makes it a what type of reaction?
You wrote 91.9.
I just wasn't done writing my 8 yet, that's all. Alright? Which makes this what? Endo. Okay? So be on the lookout, guys. You've got to be looking the forward and the reverse direction when they give you those. Number 4. What's different about number 4?
It is not proportional to the one that was written.
Okay, the one that you have written is written how, guys? C plus O2 yields CO2. This, we've got to double it, right? So the value that we get for the original one, guys, on table I is negative 393.5. But ours here in this example is doubled. So since we have 2 moles for everything. So now it's not going to be negative 393.5. It's going to be what? Negative That's what it should be when you double it. It should be right around there. Regardless, guys, it's still a what type of reaction? Exothermic, okay? Now the last one, number 5, when you look for this one took me a few more seconds to find, okay? When you look here, what's different about it from what's on table I? It's half of what's written, and it's backwards, right? So when you take a look, it's about, where is it? I'm trying to find it on table I. I had it and I lost it. I'm just telling you. Yeah, there it is. It's 2CO plus O2 yields CO2. So it's reversed, so you've got to flip it. So originally, guys, it was negative 566. No, you don't have to. It's not reversed. All right? It's negative 566.0. But you are just cutting it in what? In half, okay? You're just cutting everything in half. It is reversed. It is reversed. So you got to make it positive 566. You see how it plays tricks? I've been doing this for a while. Granted, this is a little bit newer. It's been a little while since I've looked at this chart, guys. Take your time with these, okay? Make sure I would encourage you guys to write it out. When you get to your readings exam, circle the reaction on your reference packet. So do you know which one you're looking at? That's just a good test-taking strategy. So you've got to flip it, make it 566, and we got to cut it in half, okay? So now when we cut this in half, 566 becomes what? 283. And it's going to be endo. So there's your final answer for those last two, okay? Is it super complex? No, but you've got to be careful, all right? Questions on table I. All right, let's talk about potential energy diagrams. I know we only got a few minutes left in this period. We'll get as far as we can. We can finish it up tomorrow. So, forward reaction, guys, this is basic. We know this already. Left to right, you can just put that down on the line, guys, if you want to say left to right. Reverse reactions, right to left. It's the opposite. We haven't, formally talked about it. We've just kind of informally read things forward and reverse. So we're just getting it down there. Activation energy, guys, that's a piece that we will continue to talk about a lot. It's the amount of energy needed to get a reaction started or to form what's called the activated complex of a reaction. You got to get over the hump. That's what you're looking for. And you'll see what I mean as we get into potential energy diagrams.